So this is session 2 of the P6 unit, 21st Century Science for OCR Physics. And in the last session we learned that an atom was mainly empty space with a positively charged nucleus in the centre and with negative electrons orbiting around the outside. So we're going to have a little bit of a closer look, and we're going to call this inside the atom. So let's start with the idea of a nucleus. So a nucleus consists of protons and neutrons which are closely packed together. Now, the reason that a nucleus can hold together at all is due to something called the strong nuclear force. Because if you think of these 3 protons here, 3 protons all have the same charge, they're all positive. So the protons are positive, and as you might know, that if things have the same charge, then they are likely to repel. So they have electrostatic repulsion. Opposites attract, but like charges repel each other from P5. So how can it be that these protons can exist in the same nucleus when they've got the same positive charge and then this electrostatic repulsion? So what we have to understand, first of all, is the idea of what we call the strong nuclear force. Now, the strong nuclear force is what holds the atom together. So protons at a distance have an electrostatic repulsion. They don't like being near each other. And as you bring them closer and closer together, the force of repulsion between them gets bigger and bigger and bigger. But then you reach a critical point, which if you get any closer than that, then a second force overtakes that force, known as the strong nuclear force, which is much stronger and is actually an attractive force. So the strong nuclear force allows the protons to attract each other, but it only operates at a very short range. Now, the best analogy for this is the idea of if you have 2 magnets which are both having the north poles facing each other, and you know if you tried to bring those 2 together, then you would have the magnets repelling. And as you brought them closer and closer together, the repulsion would increase and increase and increase and increase. So to model the idea of the strong nuclear force, if you imagine covering each magnet in Velcro, you could in fact bring those 2 together, and then when the Velcro engaged, then the 2 magnets would actually stick together. So the force of the Velcro is larger than the repulsion force of the 2 magnets in our analogy. So in the atom, the strong nuclear force overcomes the repulsive force of the protons. So that's what keeps the nucleus together. Now, we're going to look at some chemistry here. So hopefully you'll remember that every atom has got 2 descriptive numbers, and it has a mass number and a proton number, also known as an atomic number. Now, these numbers, as you should remember for chemistry, will tell us everything we need to know about what's in the atom. So for starters, for carbon, the proton number tells you the number of protons. So this carbon atom has 6 protons. The mass number tells us how many particles there are inside the nucleus. So in the nucleus there are 12 particles. Now, as we know, the nucleus consists of protons plus neutrons. So if there are 12 particles in the nucleus, 6 of them are protons, then it stands to reason that 12 minus 6 equals 6 of them are neutrons. Now, in P6 we're not so interested about the electrons, because the electrons are what get involved in bonding, and P6 is all about what happens to the nucleus. Radiation is about the nucleus of an atom. But just for completion, we should know that there are always the same number of electrons as protons in an atom, because an atom is neutral, so the pluses of the protons have to be balanced by the negatives of the electrons. Okay, so just to recap, it's the strong nuclear force which acts at a very short range, which means that the nucleus can actually stay together. And as you know, the strong nuclear force only acts when the particles are very close together, a bit like Velcro on magnets if you want an analogy. Also, that the mass number tells you how many particles there are in a nucleus, and the proton number tells you how many of those particles are protons, so therefore you can calculate the number of neutrons always. Okay, so that's a stable atom. Now, going on to some chemistry again, there are different versions of atoms. So for example, carbon 612 is probably the one we're most familiar with, but there is another version of carbon called carbon 14. It's got 14 particles in its nucleus. So if we just do a quick check, that means there's going to be 6 protons. 14 minus 6 equals 8 neutrons, and again there'll be 6 electrons because electrons always match protons. So this is a different version of carbon. It's still carbon because what makes it carbon is the fact that it's got 6 protons. So what makes an atom a particular element is how many protons it's got, but the number of neutrons can vary, and there are various versions of carbon, for example the carbon 14 and the carbon 12 that we're more familiar with. They both react the same chemically, they just have sometimes different properties in terms of their stability. So carbon 14, because it's got those 2 extra neutrons in its nucleus, this actually makes it slightly unstable. And so in order to make itself stable, it decays. And what actually happens to carbon 14 is it decays into nitrogen, and nitrogen is 14 and 7, and we'll deal with what happens there when we look at alpha, beta and gamma radiation. But essentially what I want to get you understanding is the idea that there can be different versions of the same element, but some of these elements are unstable, and if an atom is unstable, then the nucleus can decay. Now then, if a nucleus decays to become more stable, we say that that element, or that isotope I should say, is radioactive. So to define radioactivity simply means that you have a version or an isotope of an element which tends to decay into something else, and when it decays into something else it gives out something that we call ionizing radiation, and we'll come on to what that ionizing radiation is in the next session. But just to summarize and make sure I write that down, which is isotope. So isotope is a version of an element with different numbers of neutrons. Okay, just to recap then. There are, for many elements, there are different versions. Those versions are called isotopes, and the thing that makes them different is how many neutrons we have. In the case of carbon 14, we've got 8 neutrons. In the case of carbon 12, we've got 6. There is no right version or correct version. There are just different versions. Some are more common than others. Some of these isotopes tend to decay because the nucleus is unstable, and when the nucleus decays we say that that isotope is radioactive, and if it's radioactive it means that it will change into something else and it will actually give away some of its particles from its nucleus, and that's called radioactive decay.